On to independent variables for probability. We'll talk about binomial, right? Let's check the map a little bit, shall we? So at this point, we're still over here in discrete. Boy, did we spend a long time on dependent, joint, disjoint, all that kind of stuff. But now we're going in this direction. We're talking about independent variables, and we're starting off with binomial. That's what this video is. There's actually going to be 2 videos, at least, on binomial. What we're going to be doing is actually deriving this formula that we're going to be using. And then another video will do some examples so that you can see how it plays out. So with that in mind, we'll have to figure out what it means to say something's binomial, and we're going to do a derivation. Just to review, binomials 1, we have geometric probability and Poisson probability are all part of independent variables. So we're just focusing on binomial at the moment. So let's look at an example. A 3-question quiz. Each question is multiple choice with 5 options. Does this sound familiar? When we were doing the fundamentals, in the very beginning, the fundamentals of probability, there were 3 videos on this. We constantly used one example, which was a 15-question multiple choice quiz. You didn't know it at the time, but that was actually binomial. Well, now the question is, what does binomial mean? A variable is binomial only if these 4 things are met. Each random event has only 2 outcomes. All right, let's check our quiz here. So we have 5 options, right? That's not what we're talking about, though, right? Our outcomes are success and failure. You either get the question right or you get it wrong. It depends on what you're talking about. Sometimes it's right or wrong. Sometimes it's left or right. It's, you know, but there are only 2. The outcome of every random event is only 2. You know, a coin can be heads or tails, right? That's binomial. Right? Events are independent. Of course, we are talking about the independent variable branch of the probability map, so that the second quiz question, the probabilities don't depend on the results of the first one, right? If we're choosing randomly on this quiz. Probabilities, and again, you know, that's like the coins, like the second flip. It doesn't matter whether the first flip was heads or tails. The second flip is still 50-50. They're independent. Probabilities of the outcomes do not change. That's pretty important. So again, in this quiz, the probability of getting a question right, if you guess randomly, with 5 options, as we talked in the first videos, is 20%. Right? So what, in this case, right, P is often used to denote success. Right? In this case, it's 20%. Q is often the other side, the failure part, which, because there's only 2, is always just 1 minus the success, 0.8. Well, there are 3 questions, and all 3 questions have the same probability. Now, that wouldn't be the case if, for example, 2 of the questions had 5 options each, but the third question actually had 4 options each. Because then suddenly the chance of success isn't 0.2 for that question, it's 0.25. So then, as a group of 3, it would not qualify as binomial. And the final criteria is that there should be a fixed number of trials, n in this case, not just in this case, but n is always used for a number of trials. Now, it's been a little while since we talked about trials. When we got into dependent variables and joint versus disjoint variables, we actually didn't really do it in trials. All right, we talked about single event probabilities. We talked about multiple event probabilities, like getting 2 diamonds in a row that you pull out of a deck. Trials is another level higher of organization, which is sets of groups. You could think of, again, you could flip a set of 3 coins a number of times, right? If you flip a set of 3 coins 8 times, then n is 8, right? Number of trials is how many times the set of random events occurs. So we can now look at this question more specifically, because it does actually qualify as binomial. And not everything does. No, binomial is a very strict and very rigid set of criteria. So it has to, it only applies when these 4 criteria are met. Now, these criteria have been met for this question, this example. We filled in success, we filled in failure. Let's actually fill in. What is the number of trials for this? We have 3 questions, 5 options each. Well, I just said, trials are sets of groups. Well, as I said in the very beginning with the fundamentals, you can have a group of 1. So we can think of this question, right? One way of thinking of it is that we have really three trials, right? Each question is its sort of own group. That won't always be the case. It's not quite as interesting, but because we're doing a derivation, it's going to simplify things quite a bit. Usually you actually do have sets of groups as opposed to sets of singles. All right, so now let's get to the details. Here's our example. We have our N, P, and Q, number of trials, probability of success, probability of failure. We need a question, a direction to move in here. Create the probability distribution for this quiz. Right here, probability distribution. Again, we haven't talked about that in a while. We did in the very beginning, right? This is going to be a histogram of all the probabilities for all of the possible outcomes. We're going to have to deal with sample space. It's going to, really relate back to those fundamentals videos. Now, what we're going to do here is combine that with the structure of a tree diagram. Because what we want is the sample space. We have a bunch of events. Each question is an event. So we can create a tree diagram that will get us our sample space. Here's the start of it, right? Question number 1 can be correct or incorrect. If you got the first one correct, the second one could be correct or incorrect. If you got the first one incorrect, the second one could be correct or incorrect. I think you get the idea. And of course, here's question 3. Can be correct or incorrect. Now we need probabilities. Well, we have probability of getting it correct. 0.2, probability of getting it incorrect. 0.8. Bam, there they all are. Notice the repetition. Right? Because we only have 2 outcomes, because probabilities never change for the different events, the events are independent, there's a lot of repetition. That's why binomial tends to be the favored probability that everyone likes to use. Because with repetition, you have the possibility of an equation. Notice that with the dependent variables, there were really no equations. All we were using were, the addition rule and multiplication rule, and that was it. No real equations. Well, now with independent variables, the 3 different types of independent variables, we're going to actually have formulas, which means eventually we will not need to write the tree diagram. With dependent variables, you're out of luck. You pretty much have to do tree diagram. You're going to have to do the Venn diagrams. That's the only way to do it. We actually can be much more concise with independent variables. And that's what we're doing with this one. All right, what we're doing is we're actually deriving that equation. So to do that, let's look at the sample space now. Here they all are. The probability of getting correct. Now, I didn't write it out with the ands, right? This is correct, and correct, and correct. And that's actually relatively important, but it takes a lot of space. So this is probability of correct, probability of correct, incorrect. Again, what I'm doing is I'm just following these paths. Correct, incorrect, correct. Then we have correct, incorrect. You go through the whole tree, you get your whole sample space. All right, now let's calculate the probabilities. It should be fairly familiar at this point. It's all multiplication rule because it's all ands. All right, and this is actually a nice stage to kind of look at. Again, you can see because of all the repetition in the tree diagram, you can already anticipate that there are going to be a bunch of numbers that are all the same. Because here, look, there's 0.2, 0.2, and a 0.8. Here's 0.2, 0.2, and 0.8 in different positions, but it's multiplication. It doesn't matter. That's going to give us the same number. And look, again, 0.2, 0.2, and 0.8. Right? We'll get the same number. And there they are. And we actually only have 3 different numbers. 008, 032, that is a bunch of places. 128, that's a bunch of places. And 0.512, right? So things are going to simplify pretty nicely, and this is exactly why we are able to get an equation. We can do a quick check, make sure that we got it all. If we add this up, what should we get? Right, 1. And if you check it, I believe you do get 1. So the tree diagram is now complete and relatively familiar. Hopefully at this point in time we've done a bunch of these for the dependent variables. But now probability distribution. This is what we want. What do we mean by probability distribution? What are all the outcomes? Well, we have, let's get a new page here. We probably need to kind of review a little bit, at least refresh our memory about what probability distribution is. First of all, it's a histogram, typically. We'll do a histogram now. So let's draw a histogram. That'll help jog the memory. All right? And if you remember back from the beginning videos, what did it look like? We had a histogram that maybe looked, it was something like this, and then I think it was a skewed kind of thing. It had some, really small numbers. When it was a 15-question quiz, something like that. Example. All right. So, what's the axes? All right. We already know that the y-axis. Well, that's probability. It's a probability distribution. What is the x-axis? What's the units? What's the variable, which is the x-axis? Well, if this was, let's see, that's 1, 2, 3, 4, right? What does 3 refer to? That means getting 3 questions correct, right? In that original 15-question quiz that we started with. All right, so really, we want the number of correct. So we'll do the same thing. This is the same kind of example, kind of convenient that way, almost as if I planned it. Here. So what we want is number of questions correct. And we need the whole range, right? 15 questions in that original example. So could you get less than 0 correct? No. Could you get more than 15 correct? No. Well, oops. In this example, what's the minimum we could get correct? 0. Could we get 1 correct? Yep. Could we get 2 correct? Yep. Could we get 3 correct? Yep. Could we get 4 correct? No. There are only 3 questions. So those are all the possible outcomes. The number of correct answers, which means we have to kind of look through our tree diagram here and start picking out, well, this one? What is that? Oh, that's 3 correct. So I guess that'll go here. Right? That's the CCC. Correct, correct, correct. What about this one? Oh, that's 2 correct. CCI. CC, correct, correct, incorrect. Go through the whole table, and you get something like this. There they all are. And look what I've titled this heading here, combinations. So we have only one combination that gets none right. There are 3 combinations that get 1 right, 3 combinations that have 2 right, 1 combination that has 3 right. I use this word to foreshadow a little bit. We talked about combinations before. We have some algorithms that we can use to get these, and those will come up in just a moment. But let's kind of fill in the next column. Right? What's the probabilities? Here I've written out the calculation, and there are 3 combinations, and so yeah, the 0.2 kind of moves place, but we already talked about the fact that it's multiplication, so it doesn't matter what positions. So this is going to be true for all of them, and we already saw in the tree diagram that we all get the same number. But at this point, we're trying to come up with a formula, so we're looking for pattern, and this is going to help us find that pattern. To get a formula, we have to actually go from specific to general, right? Because will the probability of failure always be 0.8? No. What happens if there are 4 options in each question? Then that would change. So we're going to have to switch to using variables. So for variables, we'll use our Q for failure probability and P for our success probability. Now what we can do is say, oh, well, there's a more concise way of writing Q times Q times Q, isn't there? That would be Q cubed. And this could be P times Q squared. 2 Qs. But here there are 2 P's. So we have P squared times Q. And here we have P cubed. So pattern is hopefully starting to emerge. Now, to make the pattern even more clear, we should actually write a P here. Well, how can we do that? Well, there's a number in front of Q to the third. It's not usually written, but it's 1, isn't it? And in fact, there's a number out here. It's not usually written. 1. You could multiply anything times 1. Well, P raised to what equals 1? P raised to the 0. So this looks like that. If we were to write the exponent here, we don't usually write it, but what is it? It's P to the first. And then what's the exponent on Q? Right? Don't usually write it, but it's there. It's first. P cubed, just like above, Q to the 0. Well, now look at this nice simple pattern. 3, 2, 1, 0. 0, 1, 2, 3. Now that is a nice pattern that we can capitalize on and write a formula. But before we get to the formula, we have to do the thing which I momentarily forgot about doing, but now remembered. Because coming back way over here, there's a difference between these 4 rows, right? There's only 1 of these, but there are 3 of these, 3 of these, and 1 of these. Well, that's a difference in the probabilities, isn't there? If we actually look at, the total, right, that would be 6, 7, 8. Well, we know that 1 out of 8 is different than 3 out of 8. Now, that would only be true if it was 50-50, right? It's not 50-50, but that concept that because there are 3 combinations, that's going to be different than here. So we have number of combinations. All right, 1 of those, 3 of these, 3 of these, 1 of those. So when we get to our probability again, really this is going to be 1 p to the 0 q to the third 3 times that, 3 times that, and 1 times that. That's important. We won't get the right numbers unless we recognize that there are actually 3 combinations that produce this outcome. So now there are 3 parts. The exponent is actually the easiest part to work with because 3 and 3, well, there's something in the very beginning. Here we are. In our statement up here, where do we see 3? Oh, that's the number of trials, right? We have 3 questions. So what we can say is this is going to be, and notice on the p, it's the same as the n, right? So really this is our kind of our n. So, sorry, I misspoke. The last one is n. N is 3. We actually need a variable for our outcomes. And again, in that first few videos on fundamentals, I actually gave you a variable that is typically used, which is r. Right, so here r is 0. So what's the exponent on p is our variable r. Here r is 1. And look, on p is our variable r. So guess what? P is going to be raised to r, the outcome of interest. Now that gets multiplied by q. Now here it's a little different. You know, r is 0, but the exponent isn't 0, it's 3. So this actually is n minus r, and if you kind of trace it, 3 minus 0 is 3. 3 minus our r value of 1 is 2. 3 minus r of 2. 3 minus 2 is 1. Right? 3 minus 3, 0. All right, so it works. Now, the last piece is this number here, the 1, the 3, and the 3. This is the number of combinations. Well, we have a formula for that all the way from those beginning videos, which is n choose r, right? Number of combinations. Right? This will give us, our 1, 3, 3, and 1. And so this is the probability for outcome r. This, my friend, is the binomial formula. Dun, dun, dun. So, whenever you have a situation where you have a binomial variable, you can say goodbye to the tree diagram. With this, you don't need the tree diagram anymore. You can just plug in the numbers, and it gives you the probabilities. And that is what our next video will show. But before we go to that next video, I almost forgot, we need to talk about expected value and standard deviation for the binomial distribution. And these, unlike the binomial formula, which we just derived, we're not going to derive these. I'm just going to share them with you, and we can use them in some examples. So the expected value is nice and simple. It's actually just 1 over the probability of success. And when we have, or when I calculate variation, that's going to be the square root of q over p, which again is nice and simple, square root of probability of failure over the probability of success. And that gives us our measure of variation in the probability distribution.